What happens to concrete after a building is demolished? Concrete is a composite material made from water, cement, and aggregate. Producing it requires extracting and processing raw materials, which consumes energy and harms the environment. In line with the principles of sustainable development, the use of raw materials in concrete production should be reduced. One way to achieve this is by replacing primary materials with secondary recycled materials or industrial byproducts. To reduce the use of natural aggregates, recycled aggregates are applied, including recycled concrete aggregate, brick aggregate, glass aggregates, or even aggregates made from rubber tires. Recycled concrete is produced with a significant share of recycled concrete aggregate. Instead of relying only on natural gravel, sand, and crushed rock, resource-saving recycled concrete uses aggregates obtained from waste concrete and construction rubble. In this way, it systematically reduces the demand for primary resources. Using recycled concrete is also an important step towards circular construction, ideally creating a closed material cycle. The production of aggregates from recycled concrete involves several steps. First, rubble is collected from demolition sites and carefully sorted to remove contaminants such as metal, wood, plastic, and other unwanted materials. The sorted rubble is then crushed into smaller pieces using jaw or cone crushers. After crushing, magnetic separators are used to remove steel and other metals. Next, the aggregate is washed to eliminate dust and fine impurities. Finally, it is sifted to obtain fractions with the required grain sizes. The benefits of recycled concrete are extensive. By reducing the use of natural resources, it helps conserve raw materials. It also has a wide range of applications and can achieve properties equivalent to standard concrete, with the possibility of being used up to compressive strength class C30 or 37. Recycled concrete supports circular economy activities and contributes to the decarbonization of the construction industry, since it produces fewer emissions than concrete made from virgin raw materials. Another important advantage is the reduction of landfill waste, as recycling eliminates or significantly decreases the amount of material sent to landfill and lowers the costs associated with disposal fees. At the same time, production costs can be reduced, because concrete with recycled aggregates often requires fewer raw materials and less transportation. The share of recycled aggregate in concrete is strictly defined by European standards. Both production and use are regulated by EN 206 concrete requirements, performance, production and conformity, and EN 112620 aggregates for concrete. The process of introducing recycled aggregate into the mix is based on multi-stage quality control, which ensures the proper content and performance of the aggregate. According to EN 206, there are two types of recycled aggregates. Type A consists of at least 90% crushed concrete, with up to 10% made up of other crushed materials, such as masonry elements, unbound or hydraulically bound aggregate, or natural stone. Type B must include at least 50% crushed concrete, with a total of at least 70% consisting of crushed concrete, together with unbound or hydraulically bound aggregate and natural stone. The remaining 30% may include other crushed materials such as brick or silicates. The maximum share of recycled aggregate allowed in the mix depends on the exposure class of the concrete element. Recycled aggregate in concrete must also be considered in relation to exposure classes. The amount of recycled material that can be used depends on the environmental conditions to which the concrete will be exposed, as defined in EN 206. Concrete made with recycled aggregates has specific properties that depend on several factors. The quality of the final material is influenced by the initial strength of the waste concrete, the percentage of recycled aggregate in the mix, and the amount of old mortar that remains in the recycled aggregate after cleaning. Grain size and the content of fine fractions smaller than 4 mm also play an important role in determining both the workability of the mix and the performance of the hardened concrete. Concrete made with natural aggregates and with recycled aggregates does not have identical properties. One of the most visible differences is density. Concrete with natural aggregate has a density of around 2,400 kilograms per cubic meter, while concrete with recycled aggregate averages about 2,250 kilograms per cubic meter, depending on the percentage of replacement. This reduction comes from the lower specific gravity of recycled aggregate and the higher air content in the mix. Another key difference is workability. Recycled concrete aggregate absorbs more water than natural aggregate, which reduces the ease of handling the mix. To improve this, recycled aggregate is often pre-saturated with water for at least 24 hours before use. The compressive, flexural, and tensile strengths of recycled concrete are also affected. Tests show that when 100% of natural aggregate is replaced, compressive strength can be 15 to 40% lower. At all testing ages 1, 4, 7, 28, and 90 days, the compressive strength of recycled concrete is lower than that of natural aggregate concrete. Flexural strength with full replacement of coarse aggregate is either the same or up to 10% lower. Tensile strength decreases by 12 to 31%. Replacing fine aggregate reduces flexural strength by about 20%. However, replacing only 20% of natural aggregate has negligible effects. The modulus of elasticity decreases by 6 to 33% with full replacement. Shrinkage, creep, and durability also differ in recycled concrete. Shrinkage may be 20 to 50% higher with full replacement of coarse aggregates, and up to 70 to 100% higher when both coarse and fine aggregates are replaced. Creep increases by 30 to 60% depending on the level of substitution. In terms of durability, replacing up to 30% of natural aggregate shows no loss of frost resistance, water absorption, or permeability. Beyond this level, water absorption increases significantly, carbonation depth rises, and resistance to chloride penetration decreases. After 25 to 50 freeze-thaw cycles, compressive strength decreases by about 25%, and mass decreases by around 5%, regardless of the replacement percentage.